time we learn something that that's kind of like useless to him, she's like, I hope I forget that immediately. Like, I'm trying to remember. It's like,
I sometimes become very upset if I remember a physical constant, yeah.
Mm-hmm. Yeah. Alright guys, let's get started with a word of prayer.
Yeah.
Dear Father, just thank you for the way that you love us, and just for the opportunity that we have here to learn some algebraic topology. I really help us all just learn something new, understand something a little bit better through the study. In Jesus' name, I pray. Amen.
Amen.
Cool. So,
sorry to delay you
right.
through my nonsense.
I think that we ended
Sure, it'll be the last time.
Just figuring out what the reduced homology of spheres are.
Oh, yes, we were to the fun part.
Yes. And now we're just going to like prove some neat stuff. And so the first is...
today is the Everything is Awesome lecture.
Yes. So we get into the our fixed point theorem from chapter 0. So the first theorem we have is... that if n is greater than or equal to 0, then Sn is not a retract. Dn plus 1. If you guys don't mind, I'm not going to go over that proof again. Just remember the end of the proof when we proved it. I think it was lemma 0.2. We assumed that hn of dn is equal to 0 for all n. 0, and that hn of Sn, and hn of Sn is not equal to 0. And now we have that. Dn plus 1 is contractible. So hn is equal to 0.
Yeah.
For n greater than or equal to 0. And yeah, we just showed that it's not going to be the homology group of Sn is not going to be 0. So we have that, and then that gives us the Bauer fixed point theorem, which I won't even write it down. We already did it. Yes. If we have a continuous map from Dn to Dn, then there is a fixed point in that map.
Right. So the point was when we proved those things earlier, we didn't have yet the results from homology.
Mm-hmm.
We just assumed them.
Yes.
So
it's kind of like a little tease. Where that came from if you actually learn these things. Okay, and then we can show another unexpected fact theorem, 6.8. If m is different than n, then Sm is not homomorphic to Sn. And they do not have the same homotopy type. And so, proof of that is by positive, I guess. So if you suppose, if Sm and Sn have the same homotopy type, then they have the same homology.
but
we know that's not true.
well, it's mostly true.
Oh yes, it's mostly true.
I mean, the zeros match.
Okay, they're the same for all p.
For all p. That seems like a lot.
I believe you asked so much of this. Which, this is more contradiction. It's a contradiction because they don't. For example, for m.
Right.
For p equals m or for p equals n. Okay.
If m equals n, we're good.
Yes. Well, that's exactly what I'm trying not to show. Alright, another theorem with, now we're looking at Euclidean space. Rm and Rn are not homomorphic.
You know, I wonder in Lee's Topology of Manifolds book if he gets to this result by some other method.
Probably. So, again, I think it's contradiction. Yeah. So we'll suppose that there exists a homomorphism
We'll never know.
from Rm to Rn. Choose x9, the normative Rm, and homomorphism so we can call it f prime from Rm minus x1 to Rn minus f of x1. But do we have a notation for same homotopy type? I don't remember.
So the squiggle over the arrow, what are you saying there?
It's a homomorphism.
Oh, okay.
Homotopy type. So many T's and Y's. Minus 1.
How do we know that? I think we proved it before. I'm trying to remember when.
It's exercise 129.
I mean, I guess it's the stereographic projection.
Sounds right.
But generally,
Which-
whatever the generalized version of that is,
Well, oh, I'm sorry.
right?
I mean, that's,
I mean, I guess that's just what it's called, but
yeah,
I think we only went over the
the two-dimensional one.
two-dimensional version. Yeah.
But yeah, those formulas
Yeah.
scale.
Yeah, I can show that it's a deformation retract. It shows the same homotopy type.
It's pretty neat. Take 1 point away from Rn, it becomes same homotopy type as Sn minus 1, right? Hmm.
And it's the same with n, but since Sn minus 1 is not the same homotopy type as Sn minus 1, then we have n has to be different.
Guilt by association.
And
The American way.
6.10, we have if n greater than or equal to 0, then Sn is not contractible. Yeah, the proof is that otherwise it would have the same homology groups as a point. Homology groups of a point. Not. Let's see what you think. At least for Android.
I'm not disagreeing, I just can't see behind you.
Sorry.
It's okay. If n is greater than or equal, I mean, I could look at the book, but I'm too lazy.
Yeah.
If n is greater than or equal to 0, then Sn is not contractible. Huh.
And what was it? The zeroth homology group of a point is Z, right?
I think so.
And then
Yeah,
the rest of them are 0?
Yeah, and since. Right. And so, for n different than. For n greater than. Let's see. For n greater than or equal to 1, then. Yeah. So, like. Hn of just some point is equal to 0. Like for all n greater than or equal to 1. So. Which is going to be different than Hn of Sn. And then for n equal to 0.
Hmm?
Something wrong?
Not sure yet.
Okay.
I'm processing. Hmm.
Hn of Sn is going to be Z.
It's going to be Z for n equal to P.
Well,
Or I guess here, okay, yeah.
he has n equal to P there. Yeah.
Right.
And what's the sorry, just I'm a doofus. What's the significance of looking at the homology of a point on the left-hand side? If it was contractible, that means it's homeomorphic to a point.
Yeah.
Or homotopic to a point.
Yeah.
Homotopic to a point.
And so they have the same homology groups, but they don't.
Very good.
I think for n equals 0. Alright, for n equals 0,
Yeah,
I think H0 of a
Yeah.
point would be Z.
But you have Z2, right?
Right. But H0 of S0 is equal to Z2.
Z cross C to be
Yeah.
unambiguous.
Yes. Okay, yeah.
See, I wasn't like.
How is Z2 ambiguous? Well, unless you're talking. As we learned over the summer.
Yeah. No, I guess I think about homotopy, but I always think about H1. I always think about this, like circle as a circle wrapped around it, And you can't contract that to a point, but I guess, I don't know, that's, okay, fine, that's intuition, that's not.
Alright, so
Okay, so we finally know that Euclidean spaces of different dimension are not homeomorphic.
yeah, I guess that's assuming that excision is true. So I'm not sure about that.
Oh.
He kind of jumps around a lot, talks about excision, assumes that it's true and proves a bunch of stuff, proves excision, proves more stuff afterwards.
Well, it's just I guess the point is, he tries to keep it lively, right?
Yeah.
He doesn't want to
Just wanted-
do a bunch. That's basically this method of his writing, his exposition, is to not develop all of the boring stuff at the beginning, to have it kind of interspersed with interesting stuff regularly appearing, so you never go too far in a Rotman book without reading something that's not just a drudgery of development, right? He wants to keep the hits coming, so to speak.
Yeah, and so now we're going to prove excision using barycentric subdivision. And we'll get into that. Reminds us that if x1 is a subspace of x, then S star of x1 is a subcomplex of S star of x, whose term of degree n is generated by all n simplexes sigma that maps into x1. So let's look at so it says that x1 and x2 are subspaces of x. If the inclusion I think it's maybe it's J. No, just right. The maps from S star of x1 plus S star of x2 into S star of x induces isomorphisms. In homology, then excision holds. Okay, that'll remind us what excision is. Remember, we're looking at the second version. Both versions are equivalent. So I guess what we're trying to show is that I think it's going to be called K, that the inclusion, the inclusion K from x1, comma, x1 intersect x2 into x1 intersect, union x2, x2 induces an isomorphism, or isomorphisms. So that's kind of what we're working towards this one.
Cut it out. I should have waited for a better time, but I really wanted to do it. It's a weakness I have. I'm working on it, but just not there yet.
These are the same thing. Okay, so how do we do this? So proof. So we apply the exact triangle to the short exact sequences. Let's see. Yeah, to short exact sequence, 0 to s star x1 plus s star x2 to s of x mod star x1 to x star x mod star x1 plus s star x2. You guys remember what the exact triangle is? It kind of allows us to, if we have like,
Remember, we had it up in the corner over there.
right, yeah, it gives us the triangle of the homology groups that kind of can keep going around.
Oh, you is the one you said it was really more of a helix, or was that?
Yeah,
That was you. Sorry.
I think it says the projection or something.
Sorry, all you white people look the same to me.
Wow. Okay, so it says we've
I got a wow. Okay. I got a wow. Okay. Like I did something there.
You got a what?
I got a wow. Okay from that.
Oh.
So it says we obtain a long exact sequence of. I'll just go back. Page 90. Yeah, so we get like hn of
It is understandable how a person could spend their life studying homology.
yeah.
It is really beautiful algebra.
Most of it is actually just drawing diagrams. Most of my life drawing diagrams, and then kind of go to hn minus 1. And so, let's say, in which every third arrow, okay, sorry. So I is right here, I think. And so hn, or I star, is an isomorphism by what we're assuming. Right? And so every third of these is going to be an isomorphism, which by exercise 5.4 tells us that this one is going to be equal to 0 for all n. Okay. So now consider, it's in the chair. I apologize if I'm a little bit like not quite here. Let's see. So now we have this short exact sequence. 0 to S star x1 plus S star x2 x2. And then we have this map J to S star x or S star x2. And then okay. So, because this is the same, this induces a line exact sequence, and we're still going to have hn of S star x mod this, and so it's still going to be equal to 0, which tells us that J star is an isomorphism. Do you guys see that? Or should I explain it again?
So essentially, you're applying the exact triangle theorem to go from that short exact sequence to a long exact sequence.
Yeah.
Then,
And then we're
well,
gonna
you
use-
showed that was 0. Oh, and I guess the
And
n
then
minus 1 is also 0, right?
Yeah, and then when every third is 0, that means the middle one is going to be an isomorphism.
Right, because that gives you a short exact sequence.
Yeah, exactly.
Yeah.
Cool. So hn of j is an isomorphism, and so now it says consider the commutative diagram of complexes. So we have S star x1 mod S star x1 intersect x2, and we have this map K. That's the one I'm talking about up there. To S star x mod S star x2. This is L. It's just an inclusion, I think. No, yes. No, L is the isomorphism of the second isomorphism theorem. More second isomorphism theorem. It's everywhere. Right, and J is this inclusion right here. Right, and so K star is going to be equal to J star L star. Let's see. But this is an isomorphism. This is an isomorphism because L is an isomorphism. That means that K star has to be an isomorphism. And so yeah, that gives us the right, and so from this, the induced maps create isomorphisms, so we went from here to here. And so that gives us excision. That's right. Okie dokie. Alright, and now that we're there, we'll kind of like forget about homology groups for a little bit.
Can I interest you in the black marker?
Sure.
Okay. There's two right here. At least one of them should work.
Okay. So now we're talking about barycentric subdivision. And so he defines it as he kind of defines barycentric subdivision 3 times for 3 different things, but they each kind of build off on the other one because he goes from just a regular n simplex to a singular n simplex to a, I guess, or to a singular one on a convex set to a singular one on a regular space of undefined. Just harkening back to.
So he
chapter
starts.
2 a little bit.
So he's got like a story he tells her. He's like, start with a 1-point set. You can't divide that further.
Mm-hmm.
But a 2-point set we can divide in half. And the midpoint is the Berry center delta 1.
Mm-hmm.
Then basically,
Yeah. I can draw that picture if you want.
the 2 simplex, yeah,
Yeah.
that one might be worth drawing. Yeah.
And so, yeah, I think this is the most interesting one. So,
Huh.
basically, yeah, so for a point, it's just going to be a point. For an n simplex, it's going to be consist of the n faces that are the.
We can just go for the 2 simplex for now.
What'd you say?
I guess you can just do the 2 simplex, right?
Yeah, that's what I'm saying. So you start with this, and so you. Create these pyramids with the boundaries, with the faces. Then you do it again. Wait, I think.
So he, well,
Wait, I'll just go through the definition. I think that might make it clear. Denoted by SD, so this is the barycentric subdivision of sigma n. So it's a family of simplexes. Defined inductively. Okay, so we have subdivision of just a point. It's just going to be a point. Okay, and so if you have the n faces, Phi1 or Phi0, Phi1, Phi n plus 1. So there'll be n plus 2 of them. Of n plus 1. And B is equal to B is the Berry center.
that's right.
So yeah. So if we have the Berry center of sigma n plus 1, and we have these faces, then SD of sigma n plus 1 is going to be consist of all the n plus 1 simplexes that are spanned by taking the pyramid of D and the n simplexes in SD. Okay. Right, okay, so when we're looking at this triangle, we're going to start. So SD of these points are just going to be points. And then we're looking at these faces. SD of each of this face is going to be the pyramid, like it's going to be this, let's see, B naught dot E2 minus E1, I think.
So is SD like standard division or
subdivision.
subdivision?
Yeah.
Okay.
And so we're gonna, so this one face is gonna turn into two, because, so you take the bare center of these two, of this, and then you construct these two faces here. And so you do it with all of these, and then for the actual, and then for n equals 2, you're gonna construct.
So those 1, 2, 3, 4, how many other? 6. Those 6 two faces are the barycentric subdivision of the standard 2 simplex.
Yeah, so you kind of like start at the points and then kind of build up until you get to the actual thing. So it'll just be a combination of 2 simplexes. And you can show that. You can show. This is exercise 6.5. That SD of sigma n, I don't know if I should call it SD or just subdivision of, that consists of n plus 1 factorial.
Mm-hmm.
N simplexes.
Ah, cool. Like you just showed us.
Right, so if we're just looking at one simplex, I guess we can look at a 0 simplex, right? 0 simplex has 1 factorial. 1 simplex
It's 3 o'clock.
Silence.
has 2, which is 2 factorial.
Uh-huh.
3 simplex. 2 simplex has 2 factorial equals 6, and so on and so forth. Okay, erase this stuff.
That's cool. I don't know if I would have known that if you sort of find the, I want to say center of mass of a tetrahedron, and you divide it into subtetrahedrons.
Guess when to do it.
There are 24 of them.
24 mini tetrahedrons there. I would try to draw it for you, but it would blow your minds.
Yeah, I don't want to try to draw that.
Alright, so now we're looking at a barycentric subdivision of the singular chains. So we got, let's see, a convex.
See, I could get more into contest math if it was about these sorts of observations.
Then the BS. Oh,
Snake. I gotta send your contest in, Dan.
oh. I was in Miss Guthrie's email. She said there was a cash prize for the winner, and I wasn't sure if that was for this school.
Nah, yeah, that would be a good deal for you.
I'd very much enjoy getting that.
Yeah, I claimed last year's press cash prize for myself.
Not sure if you're serious.
No one come.
Yeah,
I don't remember what I was
Yeah,
doing.
there's nobody else last year. I need to pawn it off on another professor. Wahahaha.
So these generators are, I believe, the
Zero.
n simplex, the singular n simplexes.
Huh.
So basically just a mapping from
Okay.
the standard m simplex on into E. As follows. So SD, well, n equals 0. Yeah, SD 0 is of tau. It's just going to be equal to tau.
Mm-hmm.
And SD n of tau is going to be equal to tau of the n barycenter of, well, there, dot SD n minus 1 where Bn is the very center.
Oh.
Okay.
What's that dot mean? I'm sorry.
This is we talked about it in chapter 4. It's kind of like making a pyramid for simplexes. So I'm trying to remember. If there was
Like the
something.
cone construction?
Yeah, the cone construction. It's not a pyramid.
Oh, okay.
It
Okay.
looks like a pyramid, but it's a cone construction. Yeah, we'll be using that
Ooh.
properties of that a lot, so we'll be going back to that. Okay.
Neat.
And so really this is just kind of the same thing as that, but just for singular and simplexes. You kind of, so you can see like if you have like, something that maps like the two simplex onto like, into like, something like that, you'd get the same type of subdivision only in E. I guess that's not convex, so you have to, switch it up a little bit. It's not important. Okay, and then he just defines it for a regular space. If X is any space, then same thing. SDN that maps from Sn of X to Sn of X. Defined on generators. Sigma in this case. By SDN sigma is equal to induced map of sigma of SDN of this identity map on the simplex where delta n from the standard simplex is onto itself is the identity. Okay. Right, and so this is the same kind of induced map as we had seen in chapter 4, I think. Not be exactly the same. So he says, if you have this, so if SDN of this identity is equal to a sum of, like a combination of these little tiles, then, this isn't part of the definition, this is a comment, SDN of sigma is equal to sigma map of this sum, which is equal to sum of mi sigma tau. Okay, so it's so it's well defined, and it says that one may view these the n simplexes sigma tau I as the restrictions of sigma to the tau I that subdivides the image of sigma. Okay. All right. So it's all kind of a little weird, but there are some neat things we can prove about these subdivisions. So we'll get to that. Well, hopefully, Becky. Yes. Hopefully they're useful in finding excision. Alright, so we have this lemma that says that, actually I might switch back to blue. I'm sure you're getting tired of black now.
I don't think that's a politically correct thing to say.
Yeah, you're right. But I'm just against black markers. So.
So many things I want to say. I lack the life experience. Lemma 6.12. Golly. This is quite the beast we're building, isn't it?
Yeah. It's a chain map. Which, if you'll remember, that means that SD n minus 1 at a boundary tau. Or just sigma is equal to at a boundary of SD sigma. Okay, and so we're going to prove it in 2 steps since we got to look at convex sets first. Yeah, so we're just going to let X be a convex set.
Mm-hmm.
Let X be convex. Alright, and tau would be an influx of the generator. Okay, so we're trying to show that erase that. SDN minus 1 partial tau is equal to partial and SDN tau. Okay, so he says since S minus SD minus 1 is equal to 0, because S minus 1 of X is equal to 0. And the boundary map on it, 0 simplex is just 0. N equals 0 is obvious. Because, let's see.
Mm-hmm.
Yeah, it's just 0 and 0. Okay, so if n is equal to 0, or n greater than 0, I think we use, yes, we're doing induction, so we're going to assume, maybe I shouldn't always put this induction hypothesis, but I think it's helpful, that SD n minus 2 partial n minus 1 of tau is equal to partial n minus 1 SD.
You don't even need a strong induction, you just
I don't think so, since it's defined inductively, like on the previous one.
mm-hmm.
You don't need to assume it for the previous one. Let's see. Tau. Okay. So he says partial n of SD n of tau is equal to partial n. We're going to use the definition of SDN
Mm-hmm.
of tau of Bn dot construction SD n minus 1 partial n tau, boundary of tau. Okay. And then here he uses the corollary. Well, I'll just write it down. So that's equal to SD n minus 1 boundary of tau minus tau of the very center dot boundary ST n minus 1 partial n tau. Okay. And this is using what we found in chapter 4. It said the boundary of b dot gamma is going to be equal to gamma minus b dot down boundary of gamma. Okay. You guys see that? So here it's the b, here's the gamma. So we have the gamma here minus cone construction with partial gamma. So we're taking the boundary again. Okay.
Right, that was one of the lemmas we proved in chapter 4, right?
Mm-hmm. Yeah, exactly. Corollary 4.20, part 1 to be exact. Okay. So that, now we're using the induction hypothesis. We have SDN minus 1 partial n tau minus.
Mm-hmm.
Okay, but this right here. Let's see, hold on. Wait, what are we doing?
Probably using the Are you gonna?
Right. Yeah. So that's.
Oh, never mind. Well. Yeah. So that's got a partial squared
Okay.
in it. And when you feed 0 into the cone construction, you get 0?
Mm.
Okay.
So it's like it's 0. And I think that's what we want to show.
Yeah.
Okay, cool. So that's for,
Step 2.
yeah, that's for the convex convex case. Let's see.
So now you consider a singular, possibly, I guess, a singular n simplex,
Right, for just
or
the
just
general-
a n simplex as he calls them.
Yes.
Sigma from delta n into x. You're going to look at the boundary of the subdivision of sigma.
Right, so we have so sigma and simplex. So we have boundary of SD sigma. We're just doing away with indexes. Is equal to boundary of just map of SD of delta n. Okay, so that's the definition for a just for general space X. And so since sigma is continuous, sigma pound sign is a chain map, so you can switch these.
Now you use the first part.
Yeah, now since this is convex,
The old switcheroo.
and then that's equal to
Exercise 6.8a.
right, which says that if you have a continuous map, then you can switch. Yeah, so you can switch the induced map in SD. And that's equal to SD of, again, since it's a chain map, we can switch the boundary and the induced map.
Yeah, I guess exercise 6.8, and really this whole discussion is a testament to why his definition of barycentric subdivision over an arbitrary space is a good definition, because
Mhm.
it naturally lifts the subdivision on the concrete space up where we want it.
Yeah.
Yeah.
Alright, we good with 6.12?
Es bueno.
Yes, wait. Okay, so now we're at 6.13, which is also good. Great. Okay, so here he's talking about, okay, so now that we kind of have established what SD is, we're looking at what the induced homomorphism of SD is in homology. So we're actually going to show that for each n greater than or equal to 0, HDN of SD, which maps from HN of X to HN of X, is the identity. Okay. So we're actually going to go back to some of the methods that we used with like the homotopy axiom, and its analog with homologies. So we're trying to find homomorphisms. Tn from Sn of x to Sn plus 1 of x, such that boundary of Tn plus Tn minus 1 of the boundary.
So what's this lemma saying again? Like, intuitively, what is this lemma saying?
This one here?
No, the lemma.
Oh, this one?
Yeah.
So I was saying that the induced map of the subdivision is just the identity, and so let's see. Yeah, trying to think of like what like So it kind of like it changes the actual space, or it changes the complex of the space, but not like the homology. I think.
So you're saying if you subdivide the complex, you don't change the homology.
Yeah, actually change the homology. Yeah. Yep. So.
Oh, come on, do we really need to prove that?
Yeah, that's
I guess we do.
That's
Here we
pretty
go.
obvious. So. Okay, so remember we had like.
All of this we're currently doing, by the way, is part of the reason I don't actually prove the generalized Stokes theorem. And, I mean, it's not exactly quite this beastly, but it's kind of the same general can of worms. Maybe I should do it though. No.
Alright, so. If you remember, it's from. This theorem. 5.3. Okay, let's. Like where we have this weird looking. But instead of having two different spaces, we have the same one. So this one. Where this map here is going to be Tn, and then, yeah, and so on. Right, so trying to show that we're trying to find a map like this that gives this property right here.
This is quite beautiful where he's going.
Right, so looking in two parts again. So we have for x convex.
It's very cool.
Okay, so if n is equal to 0, then T naught from S naught of x to S1 of x is a 0 map. And if sigma is a 0 complex, sorry, 0 simplex, then the boundary of sigma, or the boundary of T naught sigma, because T naught 0 is going to be 0, and sigma minus SD sigma is equal to sigma minus sigma. Sigma is equal to 0. I think he defines Tn minus 1 to be equal to 0. Oh, right, because sigma, let's see, SD0 is already the identity. So we have this property right here, and so this is equal to 0, and so and Tn minus 1 is also going to be 0, I think. So we have this equality, and so that's true for n equals 0. Okay. And so for n greater than or equal to 0. Okay. So he says if gamma, which is a chain, then Tn gamma should satisfy is equal to gamma minus SD of gamma minus Tn minus 1 boundary of gamma. Okay, because that's what we're looking for. It says the right-hand side is a cycle because using induction. So we take the boundary of the boundary of the right hand side. So it's equal to boundary of gamma minus boundary of SD of gamma. Minus the boundary of this, which inductively
Mhm.
is going to be equal to 1 minus SDN, and minus SD minus TN minus 2 boundary of boundary gamma. Right, because it's still acting on boundary gamma, so that's why we have this, but the boundary of Tn minus 1 is going to be equal to 1 minus SD minus Tn minus 2.
So he's
Okay.
using the induction step not on gamma, but
But on T.
on the boundary of on boundary Tn
Oh, yeah.
acting on boundary gamma.
Yeah, exactly.
So he's replaced gamma with boundary gamma in the induction,
Right, yeah.
which is fine. That's how he gets that one there, because he's factoring out
Mm-hmm.
boundary gamma.
Right, and
Not
so
gamma,
what do we
sorry.
get here? We have boundary gamma.
You know, boundary gamma's definitely voting for Trump. Just saying.
What?
Boundary gamma.
That's right. There are
Okay.
people walking across your yard don't belong there.
SD of boundary gamma is going to be boundary of SD of gamma. So these all cancel. And then boundary, this also cancels. So this is equal to 0. Okay, so that shows that this is a cycle, therefore this is a... Let's see. Actually, we haven't defined it yet, so I'm trying to show this is a cycle. So,
Since X is convex, back to that that corollary 4.20 is
yeah, it's very useful.
the hero here, isn't it?
Four.
That's why 4.20 part 2.
Yeah, you would support that, Nathan. Sorry, it's just you know, it's sad
It's
that
low hanging fruit.
I mean, it is really sad that libertarians have been reduced to that issue.
Yeah.
Because it's really so much more than that.
Or, sorry.
Yeah, and partially thanks to Gary Johnson.
What
Yeah,
did you guys talk about?
he didn't roll it. Like Jimmy gave him a chance to roll a joint tobacco, but he wanted to show that he could roll a joint, and he refused.
Johnson?
Yeah, he actually
Oh.
refused.
I was talking about when he came to combo.
Oh, really?
Yeah, his speech performance. I think probably he might have been blazing him beforehand. I don't know. That was pretty bad
Yeah.
speech.
Yeah,
It wasn't very
at least,
cohesive.
but at least we got to hear from Ken Bone, so the important part.
Okay, so if we define this, alright, so we take boundary of
You just watch the
Yeah,
boundary
yeah.
grandma's going to go viral next year.
is going to be equal to, so the boundary of this, using what we had before, so it's going to be boundary of b dot gamma minus SD gamma minus Tn minus 1 boundary gamma. Okay, so that's equal to the inside of this. So gamma minus SD gamma minus Tn minus 1 boundary gamma minus b dot the boundary of gamma minus SD gamma minus Tn minus 1